Good morning, Chem 20s. Our lesson today is on titration. This is a continuation of solution stoichiometry, where we're going to be applying that technique into a laboratory setting. Titration is the precise addition of a solution in a burette, called the titrant, into a measured volume of another solution, called the sample solution. Titration is used to determine the concentration of substances in solution. So if we refer to our picture, in order to do a titration setup, we are going to need to place a burette into a burette clamp. This burette is going to be containing our titrant, our solution, and we would consider this piece of equipment a precise piece of lab equipment because when we look at it, our meniscus is going to just be touching the calibration line. Reminder, anything that is very thin or very skinny would be considered a precise piece of lab equipment. We're going to then be turning on our burette and releasing some of our titrant into an Erlenmeyer flask and mixing it with the starting sample solution. When doing a titration, there will be a point at which the reaction is considered complete. The point at which the exact theoretical amount of titrant has been added to completely react the sample solution is called the equivalence point. To measure this point, look for a sudden change in color or pH in the sample solution. The point when this sudden change is observed is called the endpoint. We assume it is always a one-drop color change. So when we go to use our burette, we're going to use the funnel. We're going to fill it with our titrant. We're going to take an initial reading of our titrant and write it down in our observation table. We are then going to pipette into our Erlenmeyer flask a certain volume of sample solution, 10 milliliters, 15 milliliters. Again, that would be precise because we're using a pipette. We are then going to, using the stopcock, turn on our burette and release a certain amount of titrant. We are going to stir or twirl our sample solution until we will see a one-drop color change. Meaning, as we add titrant to our sample solution, there's going to be a change in color. However, as we twirl our Erlenmeyer flask, that color is going to disappear. Eventually, when we add the perfect drop of titrant, that is when we're going to say that we have reached the endpoint. When one drop of titrant completely and permanently changes the color of our sample solution. We refer to that as an endpoint. Because our burette cannot release half a drop or a quarter of a drop or any fraction other than a drop, we will assume when using a titration setup that it is a one drop color change. Well, what I would like to do is let's practice by reading a burette. So I have two examples here. I have an example on the left of a burette, and I have an example on the right of a burette. What I would like us to do is, can we figure out how to read the burette and determine what the value is at the bottom of the meniscus? So I am going to grab pointer Q. There we go. So if I take a look here, we know my value is somewhere between 3.0 and 4.0. So my number is somewhere between 3 and 4. If we take a look, every little tick value is going to be 0.1. So if I look at the bottom of my meniscus, and again, you have to read this at eye level, so you're going to be getting down and looking at it at eye level, we would see that this value would be, well, here's 4.0. We're going to go up 1. It's going to be 3.9 milliliters. Why don't you pause the video for a second and see if you can determine the second example. So 3.0, 4.0, again, it's going to be between 3 and 4. So 3.1, 3.2, this one looks like it would be exactly 3.3 milliliters. What I would like us to do is, I would really like us to do an example of this. So here is my lab example. What is the molar concentration of hydrochloric acid solution? Now, we are going to make an observation table. A good observation table for titration comes with a title that provides information, as well as we have our number of trials. And our rule for number of trials is in titration, you are allowed a minimum of 3 trial volumes within zero point 0.1 to 0.2 milliliters of one another. That means the difference between two values, high and low, would be 0.2 milliliters max. If you don't have 3 volumes within 0.2 milliliters max, then you are going to do another trial and another trial. Now, 3 is the minimum. If you want to go for 4 volumes within 0.2 milliliters, that would be even more precise, and you would get a more accurate value at the end. So, if we read this, we are trying to figure out the titration of hydrochloric acid. We are going to record the volume of 0.974 moles per liter barium hydroxide solution required to react with 10 milliliters of hydrochloric acid. So in this lab, we are trying to find the concentration of HCl. We know we're going to pipette 10 milliliters of HCl into our Erlenmeyer flask. So HCl is going to be our sample solution. In the burette, we are going to take the funnel and we're going to put in 0.974 moles per liter of barium hydroxide. We're going to take an initial reading. We're going to then run the barium hydroxide until we see a 1-drop color change in the hydrochloric acid solution. When we do, we're going to turn off the burette. We're going to record the final burette reading in order of trial 1. Now, the difference between doing a titration lab and all other labs are, because we have to get a minimum of 3 trials within 0.2 milliliters, we are going to do a calculation in the observation table. Normally, we don't do any calculations in an observation table. However, in titration, we have to subtract the final from the initial, the initial from the final reading, because we need to know what our volume of barium hydroxide is that we added, because until we get 3 volumes within 0.2 mils of one another, we have to do another trial. So let's do a practice scenario. So I have filled my burette. I am going to take an initial reading, and my initial reading is going to be 0.6 milliliters of barium hydroxide. I'm now going to pipette 10 mils of HCl into my sample solution, into my Erlenmeyer flask, and I'm going to turn on my burette. And we're going to run it till there's a 1-drop color change. Well, when we hit our 1-drop color change, we will see that we collected a value of 15.6 milliliters. I am going to subtract the initial from the final, and we're going to get a value of 15.0. Now, the one thing you will notice usually in trial number 1 is, because we don't know when we started, if the color change will occur in 1 milliliter or 10 milliliters or 35 milliliters, we tend to do the first trial rather quickly. Meaning, I turn on the stopcock, I let it run rather quickly. The moment it changes color, I stop releasing any more titrant. Well, that means we're going to get a color change that is much brighter or farther along than it should be. Remember, we want a 1-drop color change. The moment it changes colors, we stop. That is not usually what we get in trial 1. We run it quickly. As soon as we see a color change, we stop it, but we have gone too far past the endpoint. However, we now know that our value for the volume of barium hydroxide is roughly 15 milliliters. That means for trial 2, 3, 4, and 5, we can take a look at our initial burette reading, which, by the way, our burette holds for 50 milliliters of solution. So given we're at 15.6 milliliters, that can be the initial reading of my second trial. I'm going to dump out my Erlenmeyer flask, disposing of it properly, either in the sink or a waste bucket, depending what your product is. I'm then going to rinse it out. I'm going to pipette another 10 milliliters of hydrochloric acid solution into this, and I'm going to run my solution again. This time, though, we know 15 milliliters was too far. So what I'm going to do is I'm going to quickly run, let's say, 12 milliliters, and then I'm going to release only one drop at a time of titrant into my sample solution, so that when that one drop does change the color from yellow to green, I will stop the reaction instead of letting it get all the way to blue. So I'm going to run my reaction. This time I'm going to stop it at 29.3 because I saw the color change of green. One drop color change went from yellow to green, and my value then is going to be 13.7. You'll notice it is lower than the first trial because this time we did not go past the endpoint. So again, we're going to clean up. My final burette reading will now be my new initial burette reading for trial 3. I'm going to, again, run it again. So my final burette reading is going to be 43.1. That is again going to be stopped at a one drop color change of green. We'll do the subtraction. It's going to be 13.8. You'll notice at this moment, I now have two good trials, meaning these trials are precise because they are within 0.2 milliliters of each other. Now, given my burette only holds 50 milliliters of solution and it's taking roughly 13.8 milliliters, I do not have enough solution left in the burette to do another trial. So what I'm going to do is I'm going to take my funnel and I'm going to pour more barium hydroxide into my burette, fill it back up, but that means, however, I'm going to have to take another initial reading. So when we start trial 4, my initial reading is going to be 1.2 milliliters. Again, I'm going to turn on the burette, stop it at a one drop color change. So we're going to be at green again. It stops at 15.2. My difference here is going to be 14.0. We'll notice that is not within our range of 0.2 milliliters between high and low. It's a 0.3 milliliter range. So we'll have to do another trial. So 15.2 becomes my initial burette reading. We're going to run it again, get 28.9. That's when it turned green. And my value is 13.7. You will notice in this lab data that, and I'm going to get a pen here. Here. The three trials we will be using is trial 2, trial 3, and trial 5, because those three values are within 0.2 milliliters of one another. So what I would like to do is let's answer this problem. So all the math we're going to do in a lab, that falls under the analysis section. So again, I want to take a look, and it says we are going to mix hydrochloric acid with barium hydroxide. So let's write out the balanced chemical reaction. It's a double replacement reaction, so we know the cations are going to exchange places. So we have HOH liquid plus BaCl2 aqueous. We have two hydroxides, two baby H's, two baby H's, 2Cl, 2Cl, one barium, one barium. Perfect. Now, reminder to us that when we look at this question, our job is to find the concentration of hydrochloric acid solution. So we are trying to find this, okay? Now, in the question, they tell us that we are using 10 mils of HCl. So in every trial, we pipetted 10 mils of HCl into our Erlenmeyer flask. So my volume was 10.0 milliliters. They also told me in an observation table that my concentration of barium hydroxide was 0.974 moles per liter. 0.974 moles per liter. Now, we did trials, and so we might not remember the values. And again, my values have disappeared because of this, but we are using the values from trial 2, 3, and 5. And those values were 13.7, 13.8, and 13.7. So what we're going to do is we're going to take the average of those three. So we're going to add 13.7 milliliters plus 13.8 milliliters plus 13.7 milliliters and divide our value by 3. Now, if we had 4 good trials, we would add up all 4 and divide by 4. So the average of those 3 values is going to be 13.73 repeating milliliters. Now, this should remind you of stoichiometry. Our first step is going to be we're going to find the moles of the known. So to find the moles of Ba bracket OH bracket 2, it's going to be concentration times volume. My concentration is 0.974 moles per liter times 13.73 repeating milliliters. So I'm going to just type that in. And our value is going to come out on my calculator to be 13.37626667. And I'm going to tell you that our answer is going to be recorded into 3 significant digits. And the reason it's going to be recorded into 3 significant digits is we always go back to the observation table. And so what I want to do here is let's just quickly look at my table again. And I'm going to release all my values one more time. Now, one might say, Mr. Kemp, why is it 3? I look here and the initial burette reading is only 1. Or I look here and the initial burette reading is 2. Or I look here and the initial burette reading is 3. And the key to figuring out significant digits is, 1, you look at the title. So we have 3 sig digs for concentration of barium hydroxide. We have 3 sig digs for the volume of HCl, which means my pipette was precise enough to measure to the 10th of a milliliter. And then we also look at the observation table, but you do not look at the initial or the final burette reading on the observation table for significant digits. You look at the change in volume. How much did it take for the color to change? The reason I don't look at the initial burette reading is because, Mr. Kemp, when I filled up my burette, I might have filled it up to the 0.6 milliliters. My lab partner, when he filled it up, he might have filled it up only to 3.2 milliliters, and then somebody else might have only filled it up to 11.6. It should not be dependent on where you started your burette reading. Therefore, we don't look at initial or final burette readings. We look at the change in value. So we are going to look at the volume value in here, along with the quantity we used to pipette, the concentrations they gave me in the question. So since I have 3 sig figs, 3 sig figs, and 3 sig figs difference, we are going to record all of our answers in 3 significant digits. So I'm just going to get my pen color back. So first step completed, we found the moles of barium hydroxide. My next step is going to be to do the mole ratio step. So we're going to find the moles of HCl. I am going to take 13.4 millimoles, and I am going to multiply by unknown 2 over known 1. And my value again in 3 sig figs is going to be 26.8 millimoles. Last but not least, I can now find concentration of HCl. Again, my formula, moles over volume, moles per liter, concentration. So 26.8 millimoles over 10.0 milliliters. And my value is going to come out to be 2.68 moles per liter.